It by congratulating her, who as received and got quite a bit of press a few months back. So nice one, Deb. So take it away.
Good morning, and yes, I'm going to be talking about the lunar geology session today. It's an amazing time to be studying lunar geology, and of course, over the last decade, I'm not going to linger on this slide because we're all very familiar with the discoveries that have been coming back over the last decade, but needless to say, we know far more about the composition of the moon's interior and surface more recently in lunar history than we thought possible. And then for future exploration, we know the surface temperature, rock abundance, and regolith properties across the entire moon with increasing precision as we go forward. And those are going to be very useful data products for the. And there are plans in place to continue that surface exploration in the years to come. So it's a very exciting time to be studying and highlight some of the incredible discoveries, discussions, and ongoing debates that are currently being pursued in lunar geologic research. And the caveat is I can't cover everything. We'll push forward. So some of the modeling that's been plagioclase flotation crust. So really early, as the moon is still extremely hot and giving off a lot of heat, their work suggested that beyond the terminus of the moon. And then, as Greg said, the work that I did with David, volcanic activity that, according to surface ages, would have peaked about 3.5 billion years ago, and the volatiles that would have been erupted with those lavas, the thickness of Mars's atmosphere today. So there's quite a lot of volatiles that were erupted during those volcanic Mare emplacement. And some of those volatiles may have risen of last year with using the LRO spacecraft in the low. These are phenomenal observations of bright returns, so bright albedo material of the lunar surface. And in this middle graphic, you can see some of these pixels highlighted in Shackleton crater temperature spectrum relative to the slightly darker or accessible and potentially mineable. So that's really exciting work done by Fisher et al. Another exciting discovery is the identification of, in the bottom you can see the mogonite phase of the silica dioxide component of some of these minerals being identified. And so that's really exciting. So that's being interpreted to represent water delivered to the lunar surface through later impacts and delivering that through meteorites to the Earth's surface so we can study it. But these are being interpreted as indicating water that still remains as ice in the lunar subsurface at an estimated bulk content of just over 0.5%. And this meteorite has an elevated creep component, so it's interpreted to have originated from either the Procellarum Creek terrain or the SPA terrain. So those are interesting source regions for potentially some water that's in the lunar subsurface. So really interesting observations made there by Kayama et al., published in Science Advances earlier this year. And now switching gears a little bit to the really enigmatic irregular Mare patch features that we've observed on the lunar surface. This is an ongoing debate. We haven't really arrived at a conclusion of how these formed, but there are multiple ideas out there that are being discussed. As early as 2012, Breccias et al. Suggested that they're inflated lava flows, which was also kind of championed by Stokar et al. Last year. But then there's also the idea by Chow et al. In 2017 that it could either be late-stage dike closure activity with extrusive magmatic foams forming mounds, or more recently a drained lava lake. So there's some really interesting concepts and ideas about the origin of these features that you'll actually get a chance to hear about later today as well. And then another really interesting discovery was the publication of a new WAC-derived titanium map updating the titanium map from the Clementine data in the 90s. So this was done by Sato et al., published in Icarus late last year. And generally, they're finding the recalibrated, or the new data sets suggest a generally lower titanium content across the Mare, across the major Mare regions than previously estimated, with the highest values concentrated in Mare tranquillitatis and Oceanus procellarum, with 12 to 13% titanium, and then the lowest regions lowest value regions are contaminated by highland ejecta or in the vicinity of lunar swirls, and then in Mare frigoris in the north with less than 2% titanium. So those are really useful data products for assessing the history of lunar volcanism and the evolution or not of the Mare basalt compositions. And switching gears one more time, looking at the tectonic history of the moon, recent work by Clark et al., published late last year in Icarus, investigated the newly discovered lobate scarps that they're interpreting formed as recently as 130 million years ago, so that's, or even more recently. So that's interpreted to be related to potentially ongoing global lunar contraction caused by internal secular cooling and tidal stresses. So we're still seeing that the moon is an active and dynamic place, and that's really interesting for ongoing lunar geology studies and exploration. And then I want to close this initial part of the talk by talking about how our celebration last year of the 45th anniversary of the Apollo 17 mission. We had a couple of LPSC special sessions covering, revisiting the geology of the Torres-Latrobe Valley, which was really exciting. And Dr. Schmidt also got a paper published with his colleagues in Icarus late last year, revisiting the site with LRO and M-cube data. And a couple of the conclusions that they reached in that paper included a suggestion of a tectonic source for the landslide off the South Massif instead of an impact origin. So the Lee Lincoln Scarp is a potential source for that activity rather than Tycho crater. And then also the identification of a potential pyroclastic fissure that may have been the source of the orange glass that Jack identified and collected in Shorty crater. So that's some really interesting work and ongoing continuing understanding of the Torres-Latrobe Valley, where we had boots on the ground. So we'll look forward to getting boots on the ground again, where we can really get into what the local geology is, because we're still learning so much about the lunar surface through these ongoing studies. Okay, so now I'm going to switch gears to what you're actually going to hear about today. So there's a lot of really interesting work going on in lunar geology, and some of that you're going to hear about today with new observations, new discoveries, and interpretations of data sets. So kicking it off this morning, Ryan Watkins and her colleagues are going to be talking about their use of photometry, mineralogy, and optical maturity index to characterize thorium anomalies identified in the lunar crust. So they're going to be looking at the photometric and spectral properties of these thorium hotspots identified previously, but looking to provide insight into the relationships between the soil maturity and particle size, roughness, and composition. I'm not going to steal anybody's thunder when I present your talks. I'm going to let you go and hear their exciting observations and interpretations for yourselves this morning and later this afternoon. But definitely go listen to Ryan talk about what these really enigmatic thorium anomalies are like in the surface processes or surface properties. Following Ryan, Ariel Deutsch and her colleagues Ariel's going to be presenting on these really interesting gravity anomalies in the Oceanus procellarum area identified using GRAIL data. And she's going to be discussing some potential origin hypotheses for these anomalies to get a sense for what's going on in the subsurface of the moon to cause these continuing to develop. And I look forward to hearing what she has to say about these anomalies. Closing out the morning session, Patrick Hill and his colleague are going to be presenting some work at gravity, these high gravity anomalies in the subsurface. So really interesting work that Ariel's on the Suevite formation in lunar impact breccias and comparing that to terrestrial impact breccias. So they're going to be looking at these particulate matrix-bound impact breccias and trying to figure out if they formed on the moon the same way that they formed on Earth, with the type example being Reese crater. And they're going to be doing that by investigating Apollo 14 and 16 impact melt-bearing breccias to analyze particle morphology, shape complexity, and particle sorting to gain an understanding of the melt rock phase. So some really interesting sample analyses of some strange impact breccia material and looking at how they formed both on the moon and comparing it to how we think they formed on Earth. Then this afternoon's session will start off with Jordan Kendall and his colleagues present work studying how to distinguish between primary and secondary craters at the Apollo 17 landing site. So looking, using some new approaches from modeling and observations to distinguish between these two crater types in the Torres Valley. And this is really important because it's how we characterize the surface and trying to identify where these clusters came from. It's really important to know the difference between the secondary and primary craters. So it's going to be really interesting work to hear about from Jordan this afternoon. Following Jordan, Bill Vodke and his colleagues are going to be looking at what really happened to Earth's older craters. So we all assume, I've certainly said this in talks and papers myself, is that we assume that Earth's oldest crater record has been completely erased due to erosion and tectonics, and therefore our crater record is heavily biased. And Bill is going to be looking into whether or not this is true, which is really interesting. So he's going to be comparing Earth's crater record with that on the moon, and I encourage you to go listen to his talk to find out whether our assumption of this crater record bias on Earth is actually true. All right, after Bill, Dan Moriarty and his colleague are going to be presenting some updates to their work on the compositional anomaly within the South Polacan Basin, and specifically using spectral and observational analyses to identify a source for this anomalous terrain. And that's really important because a lot of us want to go collect samples from the South Polacan Basin. We really need to know what those samples would tell us and where they came from. So this ongoing work is really important for understanding what the compositional signatures are telling us in the South Polacan Basin. Following Dan, LeChow is going to be talking about the Cauchy 5 irregular Mare patch subtypes and looking at whether or not he can link the small and large irregular Mare patches subtypes in origins. So they're going to be using these observations to decipher the origin of these really enigmatic volcanic features on the moon. So this is, again, I've mentioned this earlier as one of those really key ongoing debates about unusual surface features, volcanic features on the moon. And so Les is going to be telling us a little bit more about the observations that he's been making on these features and whether or not we can use them to distinguish the origin of these enigmatic features. So I encourage you to go listen to him give that presentation this afternoon. And then rounding out the afternoon session, Timothy Stubbs and his colleagues have been working on a very unique mission concept that involves two tethered microsatellites to investigate space weathering in the water cycle of the moon. So this is a really intriguing mission concept using small sats to study some really interesting magnetic anomalies and the lunar swirls and some fundamental processes at the moon with the space weathering water cycle. So that'll be an interesting talk to hear about the progress they're making on that mission concept and what that type of a mission can contribute to our understanding of the moon. So with that, I'm going to encourage you all to go to the lunar geology sessions to learn more about these really fundamental processes and studies that are going on. And there's a lot of really exciting observations and interpretations and discoveries being made in lunar geology. So with that, I'll, I think, answer any questions. Just make sure that your microphone's working so I can hear you.
Thank you, Deb. Thanks for an excellent and really thorough introductory talk. Really appreciate that. Are there any questions? Please do come to the mic so that Deb can hear you, if so. Perhaps people haven't had enough coffee yet.
No, that's okay.
Yeah.
This is more of an introductory talk
Right.
anyway. I should go
I think
listen to other people give this presentation.
Yeah. Oh, all right. Actually, we have a couple of people. Bill Botke is coming to the mic right now. Let's make sure it's on.
Hi, Debra. That was a really nice review of everything that's going on the moon and what's interesting. I wanted to ask you about one of the, I think, the abstracts you mentioned early in your talk. This is the one on the moon having a possible metallic atmosphere early on. Is that my recollection that they want to claim that the Earth is so incandescent right after the Earth-Moon forming event that way it affects the near side of the moon? Is that the same abstract?
Yes, I think that's right. It's a paper now, I think, but yes, that's what I was talking about.
Okay. So I seem to remember talking to Kevin Zonley about that paper, and he didn't think the Earth could ever be as incandescent as they need to get what they want. But again, I suppose I should actually read their paper rather than okay. So, but I just wanted to add. So it is a published paper now.
It is a published paper, yes.
Okay, I'll just raise that as a caveat that Kevin was concerned about it. So
that's fair enough. Yeah, it's definitely ongoing discussions about these, but it's an idea that's out there now that we can talk about because the idea is out there. So it's really interesting work going forward. So definitely.
All right, Deb. Well, thank you very much again. Really appreciate this great introductory talk.